So today I'll be going through a brief intro about what is a VLSI design flow and more about how the synthesis in terms of synthesis perspective. So I'll be talking more in details of the front end than in and some more details on the synthesis perspective. Okay. So this is the agenda for the presentation today. So I'll be having introduction, VLSI flow, linting, clock domain crossing, synthesis, and formal verification. So first introduction. So this presentation will help you to understand the complete VLSI front-end flow. So wherein I'll be explaining in detail on each of the previous agenda topics, and I'll tell you what are the tools available in the market and what exactly is the market like, what is expected from an engineer, a passed out engineer, or a MTech or a bachelor's graduate. What kind of expertise is company expecting from you? What kind of knowledge? So which tools are there which you need to learn? So those things I'll be explaining you. So this is the flow. So this is where we do the design specification. Then we write a behavior description. We put it in an algorithm fashion. Then we write the RTL description. It could be any of the VHDL, any of the HDLs. So these days we have system Verilog, and VHDL. Then we do functional verification and testing. This is what is design verification called as. This is in this we use system Verilog, UVM, OVMs, and all environment to do the testing. So when we say that our design is tested completely, there are few parameters based on which we verify that. And in this stage itself, we have few checks on the design aspect, something like linting. So linting is, I'll go into details in the next few slides. So we do some checks called as linting checks. We do clock domain crossing checks. And we do is logic synthesis, that is called synthesizing the design into netlist format. Then once we get the netlist, we check if the gate level netlist, we verify gate level. We have options for verifying gate level netlist at two levels. One is something called as logic equivalence check, which we check with the RTL. The other one is we check the gate level with the simulation. So whatever test we run at the functional level, we do the same things at the gate level. Only difference would be here is in the gate level, we run using the uh, SDF. SDF is called basically we are putting the delay. So when we are doing the functional verification, we are considering the time taken or the delays between one cell, one component to the other component, or wire travels without any delay. But in the real world, there is always a delay because of the components or because of the wear and tear of the component, right? So that's what we check in the gate level. So in gate level simulation, what we really check is whether it will work in the real world or not. Then logical verification and testing. So same things. We get the netlist, we verify it, we compare the netlist with the RTL also. Then once we think the gate level or the netlist which is generated is as per the requirement, we pass it to the backend. In the backend, we have different steps: floor planning, a place and route, physical layout, layout verification, implementation. So what is floor planning is on a die, we we will place each component depending on the what kind of component it is, whether it is high power driven or it requires more power, or how the components usage are, whether it has more input ports which are on the peripheral of the cell. So we place it near to the boundaries. Similarly to the output module, we place it at the output of the things. Then once we place it, we connect all the things. Then we do the physical layout, we check layout verification. So we are comparing whatever the output of all the steps we verify. Then we do some standard timing checks also here. Then we implement it. So this is the basic front end. So so here what we do is involves design spec, writing the code, lint checks, clock domain crossings. So inputs for these steps. So for various steps, there are different inputs. RTL, library elements, constraints for clocks, placement definitions. So RTL, we give it for lint checking and clock domain crossing check synthesis. So basically, all the front end steps need RTL for sure. Library elements are needed for synthesis, and logic equivalence check. Constraints are needed for synthesis and clock domain crossings. Placement definition is needed for synthesis. So output of the steps are netlist, and it should be similar to whatever the RTL we have generated or we have written rather. So backend step involves the, as I said, right, the floor planning, physical layout, layout verification, implementation. So input to this steps is netlist which is generated and the constraints which are generated, and output is the GDS2 file. So I'll go into the, hope you have you are clear on whatever I have told till now. So now we'll go into a little bit of linting. I'll just explain what is linting, what kind of checks we do, and what are the tools which are there in the industry. So, so what we are doing is RTL code, whether it is correct as per the rules set for a particular project. Say, for example, if we are doing this is if you're doing for a aerodynamics project or a aeronautical industry. So there, the rules and checks are very stringent. So we have to adhere to that rules. So if you're doing for a simple mobile application, the rules are not that strict as what you have for aeronautical industrial design. So based on those conditions for each project, we can set different rules and regulations. I'll give a brief some examples on what kind of rules are there. So this is done at the early stages of RTL development so that when we go to synthesis, we don't have to come back and make the changes. So it is kind of, even in synthesis step, these checks are done, but we don't want to wait till that stage of synthesis wherein we go back and recheck everything and come back and make the changes, because most of the lint errors are like small errors wherein we can avoid it during at the last stage, because synthesis is done at the almost at the last stage of your design. So what all checks we do is whether the code is synthesizable, whether code has any combo logics, whether FSM loops is like we have written a finite state machine, whether we are getting stuck in only one state, whether the sensitivity list in always module is completely written or not. So these are the few examples. And if we have a case statement, whether all the case conditions are available or not, whether we are able to write or reach all the code or not. So those are some of the examples of lint checks. So we also have wherein it checks whether LHS and RHS have same number of width, bus width. Say for example, you are multiplying 16 bit by 16 bit. So uh, on the right hand side, you have 16 by 16 multiplication. On the left hand side, if you still assign a 16 bit, it will give a error to us because the multiple the output will be beyond the uh, assigned value. So we'll be missing some of the some of the output value. So those kind of checks are done at the linting stage itself. So some of the companies and tools which are there are Spyglass, Leda, Jasper Gold. So basically major or leading industry tool manufacturer, all EDA companies are Canon, Synopsys, and Siemens. So Mentor Graphics is called as Siemens now. So Spyglass is from Synopsys, Jasper Gold is from Cadence, Lida is from Mentor Graphics. So all in all, in all these tools, the rule sets are same. So you can pick and choose what rule set you want to do based on the design and the application which you want to do. And that's how you go about it. So you set the rules, you run the tools, you check whether all the rules are. So some of the checks are like sometimes what we do is we write the code, we use some wires in the middle, but we forget to uh, initialize them at the beginning stage. So we do all those kind of checks also here. So now we are going to clock domain crossing checks. So what is clock domain crossing? So basically, nowadays all the designs have multiple clocks because we take different IPs from market which run at a different frequency, which run at a different synchronizing. So they are run at different clocks, different frequencies, different type of clocks. I mean, like it might be 90 degrees out of phase of the other clock in the design, or 180 degrees out of phase. So depending on those things, right? So as all the chips are more and more complex, we need to have different clocks in the design. So what will happen if the signal traverse between one clock domain to the another clock domain is we might have incorrect functionality. We might have validation issues. We'll not be able to see whether the data which is coming is correct, or whether we are missing any incorrect data is coming or not. So major issues which come with CDC are metastability, reconvergence, and data loss. So metastability is like wherein we check the state, the output does not reach either 1 or 0. It goes in between state. So reconvergence, data loss are wherein we lose the data, or we will not be able to reach a stable state, or we don't reach the correct stable state. So generally what we do to avoid in the design error, so when we are having, say, a signal, one signal traveling from a high speed to a slow speed domain, or a vice versa. So we use something called as synchronizers. So we have two flop synchronizers, we have three flop synchronizers. So basically what is a synchronizer is we're connecting two flops back to back. So output of the first flop, the Q of first flop is given as an input. Okay. So the data is coming from clock domain one, and the clocks to these two synchronizers are from the second clock domain. So why do we connect? How do we select whether two flop synchronizer or three flop synchronizer? So depending on how the signal gets stable. So based on that, so how it is decided is depending on the process or the technology which we are running. Okay, the design like 5 nanometer or 7 nanometer, or for that matter 15 nanometer or any nanometer, right? Depending on the technology, the signal stability will vary. So in that technology, it might be two flop synchronizer is needed, or four flop synchronizer. So three flop synchronizer. Sorry. So based on that, we use a synchronizer. If we have a vector of data, so we cannot have 32-bit or 64-bit. So that many synchronizers, if we start using, we'll have multiple issues. One is it will increase our area, it will increase our power, and also that what might happen is, as these are physical wires which exist on a device, so we might have an issue wherein some signals might come before, some signals might come later because of the delay, because of the routing which we have seen in different stages, right? So because of routing, as we are putting 64 synchronizers, so we might not be able to place all of the 64 signals together. So what we do is, the best way is we add them in asynchronous FIFO. So what we do in asynchronous FIFO is we take the data, whatever we have to transmit from one domain to another domain, we put all that data in the FIFO, write with the clock domain from where we are sending the data, and read with the clock from where we want to the source and destination clocks. So using this, we use the asynchronous FIFO. So, or we can do one other technique we can do is wherein we don't want we have a space constraint or an area constraint or a power constraint. We can do a method called as ACK and NAC. So whenever the signal, the source clock is ready, we just send a signal to the destination clock saying that clock data is available. So this is where once we receive this, the destination clock can see and submit saying that okay, I'm ready to receive. Then the source clock will send the data. So this is called ACK procedure. Then one other technique is called signal stretcher, wherein we are sending a pulse. Okay, once our from source side a process is done or few steps are done, so it has to send a acknowledgement like just a signal, a pulse. So if the source is very high speed and destination is slow, it might not be able to catch it. So that's where we use a technique called as signal stretching. So we stretch the signal so that we will be able to read it on the destination side. So this is an example of how what are the rules or checks which are there. Say for example, these are clock domain checks: configuration, synchronization, convergence, functionality, metastability checks. This is for resets. This is for when you are running an SOC design, whether consistency of hierarchical model is existing or not. And these are the some of the checks. And what is the severity? So what do you mean by severity is, so if suppose no clock association for a port something, so we have so many so how we do the check is we design a constraint file for this. So in the constraint file we specify all the ports in the design, all 100. If there are 100 ports, we have to specify the 100 ports, and we have to specify to which clock it is associated. Okay, so if any port is not associated with any clock, it will give a error to us. If it is clock is constant, it is not an error because clock can be constant, we are not changing the clock. There's a warning. If there are any clock ports which are not declared, if there is any signal which is not static or not gray encoded. So see, based on this, so we can change the severity in the design if we know what kind of code we have written. Or the other method is, once we run the whole design, we can waive them off based on whether that is a rule is okay to waive it or not. So it all depends on how you want to check in the design. So here if you see status is off means it doesn't do that checks. So now this is what a clock domain crossing is. Now we will go to formal verification. So before I jump into synthesis, I'll just give a brief overview of formal verification. Then we'll go back to synthesis after around few slides too. So basically, formal verification is what we do is, so it is a technique used in various stages. So wherein we check the RTL with the netlist. So whatever netlist is generated after the synthesis, right? So we compare that netlist with the RTL which we have written. So why this check is needed is, so we have done a design. We give constraints while generating the synthesis. While doing the synthesis, we use something called as constraints. So in the constraints, we define what is input delay, what is output delay, based on the RTL. So and we also give some like we insert DFT checks. So all those constraints when we are adding and when we are running the synthesis tool, so tool might decide that okay, whatever logic we have written, it's a redundant logic. So what it does is tool might optimize it and make it can completely remove it. So that is where we get a formal equivalence check. So what it does is it compares each point, that is output point. It's called as out points. So from each point, it goes back in the RTL or in the netlist to see and calculate what is the logical value. So if an input you give one, what should be the output value? So ideally, if in a design you have written a, say assuming you have done a flip flop, so based on that there's a combo logic and there's a flop. So if you give an input as one to this logic, assuming you have written such a code that all the corresponding inputs are ones and all, so it gives you a one at the output. So in the logical equivalence check also, or formal verification also, it does trace back from the output path and goes back and checks whether if you have given input as one and clock is one, whether the output is one or not. Similarly, it checks. So if anywhere any of these points have or even during the synthesis or any of the checks, if any of them is missing, so it will compare that and add that. Similarly, we do this formal equivalence check or formal verification at. So RTL was a synthesis, RTL was a synthesized netlist we do. RTL was a layout netlist we do. So at each stage, wherever we have a proper netlist, we compare that with the previous stage netlist so that we compare whether both are right or wrong. I'll just give an explanation on what is formal verification on both the things. So FEC, we will only talk about FEC. FPC is basically it's a property check, so it's not much done in most of the companies or most of the places. So what is it is if the design is similar to the golden design. So what is golden design? So at each stage there are different golden designs. If you see here, right, RTL was a pre-routed netlist. So this is synthesis output. So for us, we are assuming that RTL is golden because we have written it, we have done the verification, so we know that what are the bugs and all, we have fixed it. So we are assuming that RTL is golden. So pre-routed netlist. So once this is proven that these two are same, this will become our golden. So we check pre-routed netlist with post-routed netlist. So that is what the final netlist is. So pre-routed netlist, we can even compare post-routed to RTL, but it's of no use because we have anyways this we have already checked. So we check pre-routed netlist with post-routed netlist. Then we have one more check wherein final netlist versus ECO netlist. So what is, I'll just give a brief on what is ECO netlist. So once we cross the stage of, so it, so how the design matures is, so at each stage, so during the whole process of an, say SOC design, so you don't work on the whole design, you work on one module. Say for example, you're working on a mobile chip. Okay, so your team works on, say for example, there's a module called as camera. Okay, so on the whole mobile chip there's a module called as camera. So you're working on camera. So at the initial stage when the project begins, you don't give the complete camera output, right? So you slowly develop. So first you out of 50 features example, you start developing 10 features. You do at different stages. So once you finish 10 features, you give it for verification team to check whether that is fine or not. You do the synthesis, you check whether that synthesized, whatever we have written is synthesizable, whether it is synthesizing, what is the area. Because if we implement all 50 features at one time and we do the verification, it will be a very huge task for the verification team to verify all the 50 features at the same time with the time constraints we have. So we divide the stages. Say we do 10 or 20 features first, then rest of the 20 features, rest of another 20 features. So it's like 40. In the last stage, we keep it to 10 features because we will have so many issues coming from the previous 40 features, and we have so much of synthesize to do. We have to check whether the area what we want to keep our design is fitting or not. If not, we have to rework few of the things without touching the features, right? So those kind of things. So once we finish all those things, once we deliver the camera IP to the SOC team, so what happens is at the final stage, most of the time we are doing multiple iterations of the project. So if for example MI has launched one phone, so they'll come up with a different phone. So there might not be much features, but they might have seen some bugs in the original first version. They'll come up with the second version. So in that, what they do is, so they don't do the whole thing again if it is something similar. They just do a fix. So what how do they do a fix is in the netlist itself. So when we are doing the design, when we are creating a GDS, we add some extra cells in the whole design so that we can use those cells if we are missing a, say, there is some connection issue which happens, or something got short while doing the thing. So what we do is we use those components like AND gates or gates or flops, do the connections and do the netlist, whatever final netlist with the ECO netlist. So that is called as ECO netlist.